Um, in the previous video or in the previous class, we looked at blind search methods, and what we said about blind search methods was that the agent doesn't have any extra information apart from knowing the state space as well as the Go test. That is all that the agent knows. Now we want to look at another type of search, and that is the informed search. Now with informed search, what will happen is the agent will have additional information. The agent has additional information about the search space. Now this additional information, it usually comes in form of some heuristic. Uh, so the heuristic usually, which we use, is the straight line distance between where the agent is at present and the distance between the straight line distance between where the agent is and the go. So that is the heuristic which usually is used. One type of search that informed search that we use is the best first search. Okay, the best first search method. Now, in the best first search method, we have two main algorithms which we look at, and similar to what we did in blind search, where we said we just look at two methods, and then if you want to consider other methods, it will be easy to pick up. That is a similar thing that we are going to do. So in this lecture, we'll discuss grid search and the ESTA search. As usual, if you have any concern as we go on, you can interrupt and ask your question. So let's start by looking at grid search. With grid search method, what the what the agent tries to do is it tries to pick the path which appears the best at that moment. So basically what is happening is this. Let me just share something. Okay. Imagine our agent is supposed to navigate from an initial point S and is looking for a path to the goal. Now, if this agent is using grid search, what it will do is it will look at the estimated distance to the goal. So if, for example, we look at the children of S, the children of S are A and D. Now, the estimated straight line distance between A, okay, so just a minute. Okay, so the estimated distance from A to G is 11, the one that is shown inside the node. Then the estimated distance between D and G is this number 10. So when the agent is picking values to choose from, it will choose values, the smallest heuristic value from the list that it has. And then from there, that is the route that to pick. So basically what will happen, for example, in this case, initially, there's only one start node. So when the agent is trying to decide where it should go next, does it go to D or should it navigate to A? It will look at the estimated, this estimate to the goal as well as this one. So it will select D. Then from here, between the children of A and D, it says that D has an estimate of 10. So it will pick this one just like that. So now let's come back to to the presentation, and then from there, do the example. Okay, so grid-based face search always selects the path which appears best at that moment. So using that heuristic estimate, it tries to see, or as it moves, it tries to pick which route to take next based on what appears to be promising. So the estimate, like we saw even earlier, is given by h of n, which is the estimated cost from that particular node to the goal. All right, so quickly, let's look at the algorithm, and then from there, we do an example. So the algorithm is as follows. The first thing that we do is we are supposed to place the start node into the open list. So what I need to mention here is that with grid search, we are going to maintain two kinds of lists. There will be the open list, and there will also be a closed list. Now, in the open list, that is where we are going to keep all the nodes that haven't yet been expanded. So the nodes that haven't been expanded will be kept in the open list. Then in the closed list, those nodes which have already been expanded will be stored here. So what I mean by expanded nodes, that means that particular node has already been considered. So according to the algorithm, when we are starting, we are going to place the start node into the open list. And then we'll check if that is, we'll check if the list is empty. If the list is empty, that means there is no node to consider. Okay. But if it is not empty, we are going to go to step 3. In step 3, what we do is we get the node that is there, which has the lowest value of n, h of n, and we place it in the closed list. Now, by placing it in the closed list, that means we've considered it. We've checked, is it a go? If it's not, we put it there, and then we expand that node by including the children of that node. So if we have, okay. So imagine if we have a situation like this. All right. Okay, so let's say this is N, our current node. Then let's say this is P, and this is Q. So what is going to happen is we consider N, we check, is it a go? No. Then we expand it. If it has the smallest value of the smallest heuristic estimate. Now, when we move this to the closed list, what we now do, we get the children of n and put them in the open list. That is what we mean in step 4. You expand the node n and generate the successor nodes of n. These are the ones that we place there. From there, the next step that we take will be to check whether one of those nodes we have moved, one of those children nodes is a go. If it is a go, we report success. If not, we continue to step 6. In step 6, okay, thank you. I've noted that. I will change the colors. All right. Okay. Okay, so then in step 6, what we do is for each successor node, we check the heuristic estimate, and then we also check if it is either in the open or closed list. If it is not, then we add it to the open list. Then we go back to step 2. Okay, so now let us Let us now look at the example. We'll start with the example which is in your notes. So imagine we have a graph like this one, where we have nodes from A up to S, and for each node we have this h of n. Now, h of n represents the heuristic estimate. H of n represents the heuristic estimate. So, for example, from A to G, the straight line distance, the estimated straight line distance is 12. Then B, from B to G, the estimated distance is 4. There are these other numbers on the graph. These are the actual path cost to move from S to A, but in greedy search, you are not interested in these numbers which are here. You are interested only in the estimate. So the agent will be making a decision based on the estimates only. It doesn't consider the cost to move from S to A. All that it does, all that it cares for is it just looks at from where I am to the go node, which one is promising, and that is the one that it will be taken. So let's work through this together. As usual, we're going to, according to the algorithm, we'll keep two lists. There will be the open list, and so there will be the open list as well as a closed list. All right, so I hope these colors are better. So initially, we get the start node and we place it in the open list. So as we are starting, we place S in the open list. So next we check, is this a go? Is the open list empty? We've seen that it's not empty. So we are sure that there are nodes to consider. Next, since we only have one node, we check whether it is a go. Okay, so let me just put this. So in the open list, we have the node S. In the closed list, there's nothing. Now, the next step, in step 2, we said move S to the closed list, meaning having considered S and you've established that S is not a go, the next thing that you do is you take S to the closed list. Now, when you take S to the closed list, what else are you supposed to do? You are now supposed to expand S by including the children of S. Who are the children of S? The children of S here are the nodes. Sorry, I think okay. Let me just clear this. All right. Okay, so we have the open list and we have the closed list. So initially in the open list, we had S, and in the closed list, there was nothing. Then in step 2, we said move S to the closed list and, okay, sorry about that. Okay, so we move S to the closed list, and then we consider the children of S. Who are the children of S? We have A and we have B. These are the children of S. Now, we ask ourselves, somewhere in the algorithm, I think should be step 5 or step 6, we said from the children of the current node, you have to check whether one of them is a go node. So we check, is A the go? No, it's not. Is B a go? No, it's not. So now we have to choose which one do we expand next. Now our choice will be based on the heuristic estimate. So the heuristic estimate for A, we have 12, and for B, the estimate is 4. So B is more promising. So we are now going in the next step, we'll get B and take it to the closed node. So we now have in the closed list, we have S and we have B. Okay. And then on the in the open list, we have A, and now we have to include the children of B. Now, who are the children of B? The children of B are E and F. So we have E and we have F as the children of B. Now, again, we need to check from the children that we have here. A has an estimate of 12, E has an estimate of 8, and F has an estimate of 2. So F is the one that is more promising. F is the one that is more promising. So that is the one that will move in the next step, will take F to the closed list. Now, when I say most promising, what we mean is there's a higher chance that the goal will be along that path. It's not always the case, but this one appears to be more promising. When you're approaching a place, let's say you're traveling to Ndola. Initially, you are at CBU, and you start off. At some point, you get to Kafue River, to the bridge at Kafue River. Now, when you get to that point, you are closer to your destination than when you started. As you move, you get to the toll gate, then you are even closer to Ndola compared to when you were at Kafue Bridge or when you were just starting. So basically, that is what is happening. F has an estimate of 2, showing that you are only maybe 2 steps away from the 2 steps away from your goal. So we now have S, B, and we take F there. Now, okay, in the open list, we now have A, we also have E, and then we are going to include the children of F. Who are the children of F? We have I and we have G. Now, the next step, I think step 5 in your algorithm says from the children of F, check if one of them is a go. When we check I, it's not a go. But when we check G, G is actually our go. So we take this and that's what we'll put at the end. So we now have S, B, F, and G. So that is the path that will be taken. So this is how the greedy search algorithm works. I hope it makes sense, but at this point, before we go to another example, if anyone has a concern, you can now ask. If anyone has a concern, you can now ask, then we move on. So okay, anyone who has a concern? All right, hope it's okay, and we'll move on. Okay, so on Friday, I sent you this question, which I hoped we had a chance to go through. Okay. All right, I've seen something on chat. All right, there's one concern from one of your colleagues to say these heuristic estimates, h of n values, are they always given or you have to generate them? If you're implementing a system and you decide you decide to use greedy search, you have to generate some values. Let's say, for example, you're trying to come up with a navigation system, and then you're looking at, let's say, you've decided to use a straight line distance as your heuristic. You have to come up with those values. Obviously, you estimate to say the straight line distance maybe between key to point A and point B will be so much. You'll come up with those values. But if it's in an exam setup, obviously those values will be given. And the way the values will be given will be in this way, where for each node, there will be a value inside it or just near it to indicate that this is your estimate. But like I've said, if it's in a situation where your project, for example, you're implementing using grid search, then you have to come up with values. You estimate the values, h of n will be estimated. All right, so I hope that is okay. The question says, the following problem asks about the graph in the figure below. So you have this figure, and we've been told to say the children will be placed in alphabetical order. And we're doing the graph search such that the nodes will not be expanded twice. We'll try to avoid that idea of a loop, which we looked at last time. Now, the first question which we have to work on, to work out is we need to write down the order in which grid-based first search will expand the nodes. Okay, so like I've said, okay, so for now, this part, we are going to ignore this part, but we'll just work out that one. Okay, so remember, we've said in this method, we are going to maintain two lists. There will be the open list, and there will also be a closed list. Okay, so there will be the open list and there will be the closed list. Initially, we just have one value, one node to consider when we're just starting, and that is the start node. In the closed list, there's nothing at that point. Now, when we've started like this, the next step, when going to the next step, we check this one. Is it a go? It's not a go. So what do we do? In S, we take this node to the closed list. We take the node to the closed list, and then we come to the open list. Now, in the open list, we are going to add the children of S. Who are the children of S? The children of S are A and D. Okay. Next, as we go to this step, we have to check, okay, from the children of S in the previous step, is one of them a go? Is A the go? No, it's not. Is D the go? No, it's not. So now we have to decide which child we are going to expand next. So the child that we are going to expand will be the promising one. And in this case, if you look at A, the estimate from A to the go is 11, the one shown here. Then the estimate from D to the go is 10. So clearly D is more promising. So we now have S and we have D. Then on this side in the open list, we now have A, and we've got to include the children of A, now the children of D. Now, to determine the children of D, I'll come and I'll write them here, but let me just show you this. In the closed list, it's showing how we have moved from the start. So we started from S, we went to D. So from D, the children of D will be A and E. We have the children A and child E. Now, in our algorithm, somewhere we said when you are adding the children, to the list, you have to check. For example, here we say the children of of D are A and E. But before you add these children, you have to check whether they already appear somewhere in your list. So for example, here A already appears in this list. So there's no point adding it again in that list because it's already there. So we now have two children. We have A and E. Now, the nodes that we have in the open list, we have to check whether one of them is a go or not. So A is not a go, E is also not a go. So what do we do? Now we have to get one of the children, one of the nodes in the open list and take to the closed list. So the decision will look at which one is more promising. A has an estimate of 11. So from A to the go is 11. Then E to the go, the estimated distance is 7. So clearly, E is more promising. So we now have S, we now have D, and we now have E. Then this side, we have A, and we have to include now the children of E. Now, who are the children of E? So we have moved from S, we've gone to D, D, we've gone to E. Now from E, there are two possibilities. We can go to B, we can go to F. So the two children of E are B and F. Okay. The next step now that we take, we say, okay, from the children of E that we've added, is there a go? Is one of them a go? So we check B, B is not a go. We check F, F is not a go. So now we look at, okay, so from these children, which one do we expand next? A has an estimate of 11, B has an estimate of 6, F has an estimate of 3. So clearly F is more promising. So F is the one that we will bring here. So now this side, we now remain with A. We now have A, B, and we have to include the children of F. F has only one child coming from here, and that is C. Okay. So we now have A, B, C as our children. Now, to go to the next step, we'll now say, okay. Okay. To go to the next step, we'll now say, from these children, is one of them a go? We can see A is not a go, B is not a go, and C is not a go. So now we have to decide which node do we pick next. So we look at which one is more promising. A has an estimate of 11, B an estimate of 6, and C an estimate of 2. So clearly C is more promising. So on this list, we'll now have S, D, E, F, and C. Okay. Yes, D and C. All right. Then this side, we'll now have A, B. Then we look at who are the children of C. The children of C are supposed to be B and G, but B already appears on the list, so we don't include it. Then in the next step, we now say, okay, from the children of C, do we have a go? And you can see that G is a go. So we include it in our closed list, and we'll have S, D, E, F, C, G. So that will be our, that will be the order in which the nodes will be expanded here. S, B, E, S, B, S, D, E, F, C, G. All right. Okay. So I've seen there are some questions. Okay, what do we mean by a go? Remember, we're talking about go-based agents. So the agent is trying to achieve something, and what it's trying to achieve is is presented in form of a state, some desirable state. So when we talk about a goal, we're trying to look at this agent. What is it trying to achieve? If it's a navigation agent, its goal will be to ensure that it finds the appropriate path to move from point A to point B. If it is a parking agent, the goal that it will have is to ensure that everything is correctly packaged. So when we talk about the goal, we are looking at what the agent is trying to achieve. Okay, so that's how we perform this search. We still have about 5 minutes before this session ends. Are there any questions? So you now have an opportunity. You can unmute yourself and then ask a question if there's any. If you have any question, you can unmute yourself and then ask the question.
Yes, sir.
Sure.
I kind of joined in late. I want to ask, what if you have the same value? Let's say from S and as A, 11. What if you had also D as 11?
Oh, okay. So when we are estimating, or let's say when we are deciding which node to pick on, you can have a situation where the heuristic estimate here is 11, and also the heuristic estimate there is also 11. In that case, you now say, maybe you consider, you say, okay, in case they are the same, we are going to go alphabetical. Then we say, okay, in that case, we'll consider A first, and then D later on, if we don't find something more promising. So there has to be some rule as to how the agent will decide where there is a tie. And one easiest way of doing that is by saying, okay, we are going to consider them in alphabetical order. So that's one way of doing it. Okay, any other question or concern?
So there is this other part that says, show you're working using a search tree. Are you going to address that in the next lecture, or supposed to carry it out?
You already looked at coming up with a search tree. So basically, what you needed to do, if you decided to go that route, the way that you could have addressed this question would be in this way. Let me just say like this, where you say from here you go here, and then from here the next step will be that one, and then here, considering these two, the next route step will be that one. So I don't know if that addresses your concern, Owen.
Yes, sir. Yes, sir. It's clear.
Okay. Yeah, but what's important, first of all, is to know how the algorithm works, how it's determining to say, okay, I'll go this route instead of this other route. Any other concern?
Yes, sir.
Yes.
Can you go back to the diagram? I want to ask a question there.
Okay, the only challenge will be whatever I had written has now been erased. But I think we can still see.
Yeah.
For sure.
Okay. What if when we are considering the children of, let's say, E, we are saying it's the F and B.
Yes. Why?
F and
okay.
Yeah. So now you said since F has got the number is 3, which is smaller than B, so we're supposed to consider F first.
Yes.
But if in the next step we see that since A is there and the C is there, what if A had a smaller number than C? How can you connect that?
What if, let's say, as we are moving this side, we find that maybe, maybe let's say if there was some node here and it had an estimate of maybe 12, and it's the only child maybe from F. That's your concern?
No.
Uh,
What I meant to say is,
Yes.
since we are now considering F,
Mm-hmm.
the children of F, which is C.
Mm-hmm.
Now, what can we do if it happens that A has a smaller number than C?
Okay, so what that means is that the route which we're hoping was more promising is actually not promising. So we abandon this route, and then we consider A now, the children of A.
Oh, okay.
Okay, sir. All right, so we only have a minute, so instead of being timed out, I think I'll end the session here. So in the next 5 minutes, we'll start the second session. So the second session, we are going to consider A* search and then wind up. So let me end this session so that we are not timed out. And then we'll continue in 5 minutes using those details which I gave you. Okay. All right. So thank you guys for participating. I'll see you shortly.